I'll give people just a few minutes to trickle in. But while we're waiting, how many of you were here last year and heard my talk about classic machine learning? Anyone? Okay, cool. Hi, and thank you so much for deciding to spend the next hour with me on this. I hope I make it worth your while. My name is Tess. I'm a data scientist and developer. I've been a developer for a long time before I started with data science, but I started with data science around 2 years ago at Microsoft. And since then, I've been working mostly in Python, doing machine learning models, but still calling them from C# and things. And what we're going to talk about today is deep learning, so neural network in essence. But we're going to start a little bit where we left off last year. So last year I was talking about classic machine learning, so the predecessor of deep learning. Deep learning is kind of like a little bit become the de facto way to do machine learning nowadays. And I started off by showing these two pictures because what we're going to do today is we're going to create a classifier that classifies chihuahuas and muffins. And these two are there's one picture of a chihuahua and one picture of a muffin. Not going to say which one, but does anyone have any ideas? Who thinks this is a muffin? Okay, great. We have an intelligent crowd. For example, you're going to be my domain expert. What makes you think that this is not a muffin? What makes you think it's a chihuahua?
The eyes.
The eyes? Someone else? Some more experts? Yeah? Excuse me? Yeah. Eyes. Fur. Yeah. Eyes, fur. A couple of things like that. We have a lot of experience in distinguishing between chihuahuas and muffins. And about 20 years ago, around at the same time that the Gang of Four were kind of establishing the standards for software engineering, we were doing expert systems in AI. This was in my college days. I was doing expert systems where we had an expert like you guys say, these are the rules that differentiate these two things. Let's write down the rules, and this is going to be our AI. These things are still around today, but we've come a long ways since then, I think. Because one of the problems with having a domain expert kind of decide the rules is that you have to come up with a lot of rules. And you're kind of screwed when you see something like this. And then, yeah, we talked about this last year too. But obviously, then you have to decide, you have to find some kind of deeper meaning in the images, something that's a little bit deeper than maybe a few lines that say fur and eyes and ears and things like that. So we're going to get to how we're going to do that. Last year, I also talked about how to do classic machine learning in the context of house prices. House prices is kind of like the 101 of machine learning. And for me, it's kind of personal because I've been saving data around houses for 10 years. I've been figuring out basically what a house is actually worth. And I'm happy to say that last week I closed on a house, so I no longer need my data. My realtor was a little bit concerned when I brought up my Jupyter notebook and kind of showed her why I thought my house should be priced like this. But we're good. But if we look at the context of a house, and this is sort of just like a recap of classical machine learning to get you warmed up before the deep learning. What machine learning is about is, in most cases, looking at something we want to predict, a target, like the price of a house, for example. You have some input data that you're going to map to the output data. So say, given this input data, I'm expecting this output data. The more information you have coming in, the more patterns machine learning can find in your data that kind of says that this output is a good match to this input. And all you're kind of doing is, like if you wanted to do it the same way that we just did with the chihuahuas and muffins, you could have an expert tell you that this is the mapping. This is our function that will transport us from input to output. Like someone, a realtor, maybe come up with some numbers like that. Or we could have the data show us basically how we should come up with the numbers, because it turns out that this is just a mathematical equation, like some weight times some parameters plus some weight times some other parameter. And if we look at these two parameters, like the area in square meters and the price of the house, and we plot out the result on the dots, we'll see that in the case of house prices, it usually has quite linear relationship. So we're looking to create a model that's essentially a line. So this is the basis of classic machine learning. This is called linear regression. And the way we come up with this line is like this. We start off with a random line, and then we have this curve that tells us how wrong we are. So how far off are all the dots from this line? Basically, if I would use this line as my model or as my function, how far off would I be? And we want to optimize and try to create a line that gets us to the lowest possible error. So we're optimizing, and this particular thing is called gradient descent. I'm just telling you this because this becomes the basis of deep learning. But this is basically all the math you're going to need for this. Just remember that we have some way of measuring how bad we're doing, and we're trying to optimize how bad we're doing. That's the whole sort of everything that machine learning does. So we come up with this function, we come up with the weights for the line, and we now have a function that the machine decided. But the problem is that while it might seem like there is a linear relationship, we all know that there's a lot of things that can affect the price of a house. Like, for example, it's a linear relationship unless you have a pool, because then you might have a higher price, or unless you have, for example, in this case, the size and the number of bedrooms kind of tell you that it's a good family-sized house. And big houses work well in neighborhoods they're close to schools and close to some other things, where small apartments work well where there is like a lot of bars and a lot of things for young adults. So it's not linear, and you have to kind of figure out what are the features you can kind of cram out of this data, what kind of feature extraction can you do. And again, you have a human that has to go through and like come up with all these features and relationships for you to make it a linear relationship in the end. But then enter deep learning. So deep learning is when you put a lot of these linear regressions together, like you basically create a big grouping of them. Every single one of these dots, which is called a unit, a hidden unit in a neural network, is essentially just a linear regression. So it's doing the same optimization. In this case, we're looking at a neural network that has 3 layers: an input layer, a hidden layer, and an output layer. And the more layers you have, the more abstract features like family size or school quality and things like that, the machine learning algorithm will come up with. So the more the more layers you have, the more abstract it gets. But you also have a boundary where the more layers you have, the more specific details it can come up with, saying, for example, that a 3-bedroom house on this road at number blah, blah, blah is like $300,000, whatever. So you have to be careful, because at some point you're going to learn some very specific things. Either way, this is a neural network in space. And if we look through the 3 types of machine learning or AI that we've been showing here, we have expert systems, we have handcrafted rules. It's very explainable, but also very labor intensive. Then we have classic machine learning, where we come up with handcrafted features, and then the machine learning algorithms comes up with the mappings, kind of still quite labor intensive. And then we have deep learning, where the deep learning comes up with the features and the mapping. So it's not labor intensive, but on the other hand, it's very data intensive, because to come up with all these relationships, it now has to come up with them from the data itself. And we can go deeper and add more layers, and it will come up with abstract features. And if you look at it from another sort of viewpoint, an expert system, because we come up with all the rules ourselves, we know exactly what made us think that this was a chihuahua or a muffin. But at this end of the spectrum, where the machine learning algorithms come up with everything, we don't know if it was the background, or if it was the foreground, or if it was the eyes, or the paper cup, or whatever that came up with the conclusion chihuahua or muffin. So it's less interpretable, and we need to take care of that somehow. So we kind of now know sort of what deep learning does as a basic point, but there are some things that are very, very magical about deep learning. When I say magical, it's still going to be math, but it's magical like the things that we can actually achieve with deep learning. Because in regular classic machine learning, we can deal with structured data. We can deal with data that's in a tabular format, and that works well. And we can do that in neural networks too. But with deep learning, we can deal with spatial relationships. So we can deal with images where it does matter if this pixel is close to this one or not. For example, in the same with music or a voice or something like that, where it does matter how they are related to each other. And we can also work with sequences. So for example, sequences of words, sequences of like temperature that is dependent on what the temperature was yesterday or just recently, or for example, things like sales forecast where the sequence is important. We can capture that kind of knowledge also in neural networks. So this is something we haven't been able to do before. And I should say neural network really started to become a thing like 2012, but I think just recently, like around maybe last year or the year before, is where we've seen the huge advances that will take us to the point where we're gonna just get like pre-fab modules that we can use in even without training them ourselves. Now, if we look at a neural network, one very interesting thing about it is that at this point, or I should say, any of these layers actually becomes something called an embedding. An embedding is like an encoded version of whatever you're entering. So for example, if you're entering an image, this is now an encoded version of your image. So an array of numbers that represents your image. This was kind of like something that when I discovered this, things became so much clearer in deep learning, because what this means is that if you know that this is the encoding for a chihuahua, or if this is an encoding for my face, or something like that, you can then save this away, for example, in a database or somewhere else, and just use that encoded version of the object we're extracting information from, and use that in all sorts of ways. So that is a very powerful thing. One example of this is if we take this cat, we now pull it down to its like smallest encoding. We can now either choose to do a classification based on this, saying, is this more similar to encodings of cats or dogs, or something like that. Or we can tack on another neural network that does something very special, that generates instead of encodes. So we do the opposite of this original neural network that kind of got us down to an encoding. We can now decode and maybe generate another picture that looks kind of like the first one, but in this picture, every pixel is a classifier that says this particular pixel is a piece of a cat, or this particular pixel is a piece of trees, for example, which means that we can now use this to remove background or to do all sorts of things like that. Or determine, for example, if we do this in a satellite image and find out where there are houses, we can see, okay, what's the density of housing in this area from the satellite image, or whatever it could be that we're trying to segment out. So this is a quite powerful feature that we can combine an encoder and a decoder. In this case, we're encoding a message, and we're generating a new message. So we're encoding an email and generating a possible answer to that email. Or we can take something like encoding a picture and generate a caption. So the combinations we can create, kind of like Lego blocks, is amazingly powerful with deep learning. I was talking earlier about creating like encodings, for example, for faces. So this is FaceNet from Google. Basically, a way to encode my face in 128 bytes. So my face is now an array of 128 bytes. And we can see all these colors are dots of encodings of the same person, but different pictures of the same person. Now it's 128 dimensions, but projected into 2 dimensions, kind of similarly to you take a 3D world and you project it to a 2D TV screen. You can still capture most of the information, but this is a similar representation, except for we've gone from 128 dimensions to 2. The cool thing about this is that, as you can see, they cluster quite nicely together. In fact, I'm going to show you all the pictures of the people here. And these embeddings are also super powerful because we can use them to split different, they quite well encode like semantics about the person, like maybe if it's a female or a male is something that we can kind of distinguish from something like this, or it does kind of build in like meaning. Now, one thing that I should point out here, and I will get to this a little bit later, is that all of these are very dependent on whatever data they are trained on. And it's kind of a well-known thing that face detection is trained on, unfortunately, data that is not representative of the whole population. So one effect of that is actually a data set is very male and very pale because it's trained on data from Yahoo News or I shouldn't say, it's benchmarked against data from Yahoo News from 2008 to 2012, which means, for example, for females, I'm very happy that it classified me as 26, less happy that it classified me as a man. But things like that happen because it hasn't seen enough women compared to men and things like that. So when we create these systems, we have to make sure that our data is like inclusive and representative so that it learns the right things. We can also do word embeddings. So word embeddings is basically encoding a word. In this case, we can see, so this is quite powerful for a lot of different applications. So in this case, we can see that these are words that are very similar to each other: happy, excited, overjoyed, thrilled. Disappointed shows up here because it's in the same kind of region of words as the other ones. But you could think of using the word embeddings in whatever context to where you would need similar words, like synonyms of things. And we can also, from the embeddings, get relationships like man is to king, as woman is to queen. So if they have the same vector between them, they will have the same relationship. So these embeddings are extremely powerful, not only for machine learning, but once the models are created, you can use them. You can use this knowledge in your applications and actually make use of that. Another cool application I wanted to point out before we get into the practical aspects is this is NVIDIA. So NVIDIA has a big stake in machine learning because the NVIDIA GPUs are basically the only thing we do machine learning on. Most machine learning frameworks only run on NVIDIA GPUs. But they've created this generator that generates faces of images. So if you look at these images and you think that these faces do not exist, like these people don't exist, these people are completely computer generated, you start realizing like the power of these systems. I think this is amazing. Okay, all the cool things that we can do, but how do we do it? So a convolutional neural network is used for image processing or image classification. And we're going to do image classification, like do the chihuahuas and muffin thing. So the first thing you do is you train it with a lot of images of the things that you want to be able to classify. And when you go through sort of the classification, what happens is I throw in a picture of a cat. I can't draw chihuahuas, so I have to use cats instead. But in the first layer, for example, it may extract some simple features like lines or colors or things like that and mark that this region of the image contains like a line, and this region of the image contains a color and things like that. And then it combines them to more abstract features, and it might find regions of faces, or it might find regions of tires on a car, or in this case, maybe ears or eyes and things like that. And eventually, it will combine all these together and say, you know, I found like all these things that made me think it was a cat, and this little thing that made me think it was a muffin. So it's like a 91% chance there's a cat in here. And that's sort of what machine learning or what convolutional neural networks do. So the word convolution comes from just a matrix multiplication. It's a mathematical term, but in reality what it is a filter. You've seen it probably lots sometimes before where you used, for example, do a Sobel filter that will extract like the lines of a face or something like that, or it could be any type of a filter really. And it doesn't really matter because the part that the machine learning algorithm does is come up with these filters, so you don't have to come up with these filters yourself. Way back when, we would come up with these filters, just like we come up with the features in classic machine learning, but with deep learning, the deep learning comes up with the filters. Max pooling in this case is a way to compress the images. You basically just take, for example, 4 adjacent pixels and say, did I activate any of them? Did I find a straight line in any of these? If so, I'm going to say yes, and then compress, and basically you now have a smaller picture that has a yes or a no for if you found a line in this region. But the whole point of this is that this convolutional part extracts the features. That's the part that basically finds all these abstract features. And then we tack on a classifier that basically says, is this a cat? Is this a muffin? Or is this a chihuahua? So the filters could look like this, like finding like top lines or to find colors or something. But you don't have to worry about the filters. It's just sort of a representation. So this would be the output of once you've gone through the first layer. Like it will show these images as the input to the next layer instead. So if we look at a visualization of this, here, go ahead and, so I'll draw the word 3 or the number 3, and this one, for example, is a filter that detects diagonal lines. So you can see, like the closest part of that picture shows the filter. And it will then generate a feature map with like the diagonal lines represented. And this one shows diagonal lines the other way, and so on and so forth. And then we have the compression, which basically just compresses that image. And then the next stage, you can't really see it as a picture anymore, but this is an activation that shows, hey, was there, a nose in there, or was there all these things? And then compress again, and then flatten it out. So this is where we start doing the classification, and eventually we get to the number 3 in here. So this is basically how a convolutional neural network looks in action. Let's see. But how do we create one of these? So we take pictures of chihuahuas and pictures of muffins. And the first thing we do is, so this In this particular case, I've taken 500 pictures of chihuahuas and 500 pictures of muffins from searches on the internet, and I separate them out into 3 different portions. The first one, the biggest one, is going to be our training material. So that's what the machine learning algorithm is going to learn from. Then I have one section, maybe 10 to 20% of the data goes to validation. And this is because we're always kind of going to learn very, very specific things from the training material, but we also want to make sure it generalizes and kind of can be able to classify images that it hasn't seen before. So we have to validate it on validation data. And then we'll go through a loop and do this a couple of times and try some new things. And once we're done with the whole process, we'll then go over to our test data and validate it one last time. And normally, if you're doing something like this, you might have training and validation data that comes from the internet, maybe quite clean-cut pictures of muffins and chihuahuas, but then you want to be able to classify something like blurry pictures that a user takes on a mobile phone, for example. Then you want your test data, your ultimate data, to be very close to what the user is looking for. So you want quite large numbers in the training and validation. Now, I should say 500 is not a large number at all, but there are ways to make 500 pictures work, and we'll get to that. Because oftentimes you don't have a lot more than that. So the first thing we do is we're going to basically use, in this case, we're going to use something called Keras. It's a framework in Python that does deep learning quite easy. And we're going to take and train on batches of, in this case, 20 pictures at a time. So it's just going to draw a random set of 20 images from the training data. Some of them are labeled with 0, that's the chihuahuas, and some of them are labeled with 1s, which are the muffins. And then we'll just pass them through all these things where it finds the features, it compresses them, finds the features, and so on, and classifies them, and then says, how wrong are we? And then go back and sort of fix the linear regressions on the way back. And we build our network, so this is the network we want to build. First some filters in the beginning, some max pooling, then some more filters, max pooling, and then a dense and another dense layer. So this is literally how easy it is from a coding point of view. The coding is not hard, the data is the hard part of machine learning. But here we have 32 filters that are 3 by 3. And the input shape of our images is 150 by 150. Max pool, and then we add on another 64 filters, do another max pool, flatten it out. So flattening means that we basically put all the pixels in a row. So if we have a picture that's like 28 by 28, we just put 28 plus 28 plus 28, and so on and so forth. And then you just add another layer, the dense layer down here. That's the classification layer. And finally, we add on our output layer, which is, in this case, something called a sigmoid. A sigmoid looks like this, like an S. And anything that's going to come out of a neural network is going to be a number. And what we're saying with the sigmoid is, if it's a very low number, we're going to guess 0. So we're going to guess chihuahua. If it's a very high number, we're going to guess muffin. And basically, the closer it is to the middle, the more unsure we are. So at this point, we're 100% sure. At this point, we're 50-50. And at this point, we're 100% sure that it's a chihuahua. So we get probabilities on top of the selection as well. So this is basically the architecture of how it looks like. And here we can see something interesting. We now have 42,000 pixels or parameters that we can look at. So there's 42 million places where we can store little bits of data. And that's a lot, especially if we have little data to work with, because now it could, for example, store things like, if I have a white pixel in the first square, and then I have a red pixel here, then I know it's a Chihuahua because that was the only, like that combination only worked on Chihuahuas. So it could learn some very, very specific things, and that is why we need validation data to make sure that we're not just learning like weird things and that won't generalize. The next thing we do is we compile it, and we compile it and say, in this case, we're going to do a binary, like 0 or 1. So we're going to use a loss function, like this orange curve. It's going to be something called a binary cross entropy. It's just a matter of like determining how wrong we are. It's, if you will, it's just basically saying, if you guessed 1 and I said 0, where this is going to give a 1, and if you said 0 and guessed 1, then it's going to give a -1, and then we take some logarithms and a couple of things like that. Don't worry about that. That's a standard way of measuring how wrong we are. And then this LR, learning rate, basically just tells us how fast we go down this gradient with this blue dot here. And the final one is that we're going to look at accuracy. So accuracy means how many did we get correct out of the whole set. And then we now go through and train it. And in here we're saying we're going to take 20 passes through the data before we're happy. So we're going to try and learn from the data and then learn again and again and again and again and do that 20 times. Normally, if you're not happy after 20 times, you might do another 20 times, and you can just continue on the same run, so to speak. So we run into, or we get something like this. So run number 15, oh, here I did 30. Run number 15 of 30 looked like this. A couple of things I want to point out here. The first one, this is the time it took to do one run through the data. I'm pointing this out. This is 16 seconds, and this is on my Surface Book with a GPU, like a 1060 graphics card. I'm pointing this out because a lot of people think that it's going to take a long time to do deep learning. It doesn't necessarily do that. Specifically, if you don't have a lot of data, it doesn't take a lot of time. If you have millions and millions of pictures, yeah, it will. But you can also do deep learning on a decent machine, specifically if you have a GPU in not so long. The other things that are interesting here are, this is the metrics for the training data, and this is the metrics for the validation data. So the loss is basically, what's the difference between complete accuracy, or complete, like, no errors at all, and what errors we got. And we want to kind of like make this as small as possible. That's what we want to optimize for. Accuracy, again, is how many we got correct, like how many % we got correct. So we can see we got an accuracy of 98.65 on the training set, but 91% on the validation set. And we want to specifically look at the validation sets. That's the only thing that's important for us. So we're here, but we see something that's a little bit weird, and that's if we look at the validation and training data, there is a big gap between where we end up as far as like how good we're doing on the training and how good we're doing on the validation set. And this is the nemesis of all machine learning or all deep learning. It's called overfitting. And it basically means that we learned something about the training data that didn't apply to the validation data. Maybe we learned that like all of our dogs in the training data were sitting on a grass background, but they weren't in the validation data or something like that. So this is normal, but we need to do something about it. So what could we possibly do to fix this? Any ideas? Like how could we learn a more general, yeah?
Reduce the number of neurons that you
Yeah, reduce the number of neurons, very good.
generate more training data.
Generate more training data. Have you seen this before? So, generate more training data is the first one we're going to be looking at. So, we could be gathering more training data. If there is a possibility, we should always try to generate or like try to gather more training data. But sometimes that's not possible, and even if it is possible, we can do something else with images, and that is called data augmentation. So what we can do is we can take every image and say, hey, just alter it a little bit, flip it so the dog is looking the other way, or skew it a little bit, like transpose the picture a little bit up or down, or maybe tilt it a little bit at an angle or something like that. You could even add like a color filter or something. As long as it's still a dog, we're still good. And usually they're, in all these frameworks, this is automatic. You can say, I'm okay with you doing like transpose and flip and all these things. In some cases, it doesn't make sense to do that. For example, if you're looking at a satellite image, it doesn't necessarily maybe make sense to tilt it or something like that. That would not be an okay thing. But for objects like chihuahuas, it's totally an okay thing. So now we're suddenly at a point where we have tons and tons and tons more pictures than we had initially. And what we're also learning from this is that we're learning that dogs don't necessarily always sit facing this way. Even from the same pictures, we can learn dogs that are facing both ways or that have a slightly different posture. So that is one way, data augmentation. The other point is what you said, remove some of the neurons. Make this a little bit stupider. So randomly, every time we do a run, every time we do a pass through a new batch of data, we're going to randomly remove some neurons. So we might remove the neuron that remembered the color red. We might remove the neuron that remembered like diagonal lines. Who knows? In this particular pass, we might have done that. And then we have less of a risk that we're learning very specific things about this. We have less of a risk that we're learning like a red dot in the center here. So this is called dropout. And this is one of the ways that we're also making everything more reliable. So now we can train longer before we've learned all the specifics, and we end up with something like this. So after, say, 30 times, we get to a point where we're good about the training data, and our validation data also looks very, very similar to our training data. But we might be also at a point where we haven't gotten all the way there. So we're now at 93.6% or so. The next step to get this even better would be to get more and more data until we can learn a lot more general behavior. But there is something else that we can do. Actually, before I get into that, let's take a look at measuring first. So this is something called a confusion matrix. And what it's showing is, out of the chihuahuas and muffins, out of the chihuahuas, we classified 92 of them correctly. Out of the muffins, we classified 86 of them correctly. So one thing we can do now is take a look at these were the chihuahuas that we classified correctly or most correct. Muffins, these were some that we didn't classify correctly, and these were some muffins that we didn't classify correctly. So now we can take a look through the ones that we misclassified and say, hey, was there something about them that, we don't have enough spotted chihuahuas, for example, so we can't recognize that kind. We also see, for example, in this case, that we have some weird pictures, like this one. So maybe we should clean up our data set and not have things that don't apply like that. Or here we have like a green muffin. That's maybe not something our classifier has to be able to classify. So there's a manual kind of looking through the data and see. But we can also do something that's going to boost our productivity a lot. And that is using pre-trained models. So in this case, we take something, so this is in a convolutional neural network. This particular architecture is called VGG16. But it's been pre-trained with a data set called ImageNet. ImageNet is like millions of images of everyday items. And it's already done like all the encodings. It's already learned like all the features, and it's very good at encoding images of everyday objects. So what we do is And this actually outputs 1 out of 1,000 different classes: cats, dogs, chairs, lamps, whatever. And we can just remove this part, tack on our own classifier that only classifies chihuahuas and muffins, still using like all the knowledge that is gathered from all these million things. And then we say, don't train this, just give us the sort of like the embedding, like the encoding of the image, and then I'll do the classification. And suddenly we can use the training of 1 million images while only having to do the learning on the chihuahuas and muffins. And doing something like this means that we're going to take like around a second per epoch, like around a second per pass through our data. And we're going to gather all the knowledge from before. You can think of it as everything you've learned through a lifetime, you can apply to maybe, like you can apply a lot of it to a new task that you're given, because a lot of it will still sort of apply to the new task, and you don't have to learn like everything from scratch. And when we do this, we'll see something like this. This is even with our 500 images. So we end up with like an accuracy of 99.47, which is humongously good. It's like awesome, mostly because ImageNet contains a lot of chihuahuas and a lot of muffins. But in general, everyday objects learn a lot from this thing called transfer learning. So transfer learning is like a key element of deep learning that you should definitely employ if you're doing deep learning. Now, I should say also 99.47% here. With the amount of data I have in my validation set, that means I got 1 wrong. And sometimes when I do a run like this, I get 0 wrong. So we're up to like close to 100%. Now, that's how you do deep learning. So you could, if you don't want to do this model by yourself and you just kind of want to reuse the knowledge of ImageNet and everything, you could use prefab, like computer vision cognitive services, for example, where you can just enter a chihuahua and it will tell you all sorts of things, like it's a dog, it's indoor, it's cute, blah, blah, blah. Like this is just an API that you could use from any of your applications today. And you could also, if you have some specific, like you have a need to specifically look at chihuahuas and muffins, we all do, and then you can take and do transfer learning. And transfer learning can be done with something called custom vision, in which case you upload your 500 images of chihuahuas and your 500 images of muffins, and it will learn the specifics, and now you have a classifier, an API that will just say, is it a chihuahua or is it a muffin? Is this, whatever you want to classify? Is this actually a good insurance claim, or is it not? Maybe that's what you want to classify, and then it would do something like this. And it gets you get the information about how good it is, and you get an API that you can call. I'm just pointing this out because it's not always necessary to go to the point of like dealing with this thing in Python. You could actually just use the prefab thing. But either way, you want to now go through and learn what the heck did this model learn? Did it learn like the white and red pixels, or did it learn something useful? So I put a quick lesson in critical thinking. So sometimes you'll hear about these wonderful systems that give 100% accuracy or like 99% accuracy, and it's wonderful, and it's like, you're going like, it's computer said that, so it must be true, and all of that stuff. And I want to kind of give you some critical thinking to say, if you just take it one more turn, like maybe not believe everything you hear. Let's say we look at the system that's going to look at credit card transactions. So we're going to look at 1 million credit card transactions. We have 200 fraudulent transactions in this. And we want to create a system that can give us like 99.99% accuracy on finding out if a transaction is fraudulent or not. What would be a good way to start? What would be some good features, for example, or? yeah, age of person, the location, did you maybe do 2 transactions, like one in one country and one in a different country? All great things. There's a super easy way to get a 99.98% accuracy on this data set. And that is by saying every transaction is good. Right? If we say every transaction is good, we're at 99.98%. Awesome. Is it? Maybe not. We're not catching in a single fraudulent transaction. So be careful if people talk about accuracy, because you don't know how skewed the data set is. Accuracy is kind of only relevant if you have a data set that's like 50-50. So what could we use as a measurement? Maybe we want to measure like how many of the fraudulent transactions we catch. That could be a good measurement. So a good way to get 100% on that is by saying everything is fraud. Then you have 100% accuracy on all the fraudulent transactions. So you have to instead do a combination of this. I just wanted to point this out as an example because it is extremely important to think about what you measure. And accuracy, and a very high accuracy, could either A, mean that you're overfitting, you've learned too much about your training data. It could also mean that you're measuring the wrong thing. It could mean that you're actually learning the right things, but there is a big chance that it doesn't. The other thing we have to be careful about is correlation versus causation. So deep learning will find a pattern. If there is a pattern in the data, we will find a pattern. We will find the red dots and the white dots and everything. But sometimes you might find things that are not necessarily exactly what you're looking for. So a while back there was a project at Microsoft where the objective was to find out for people with heart disease, should they be inpatient or outpatient? Basically, should they be treated in the hospital or not? And what were the chances of surviving in either case? And they found that people that had asthma had a very, very high survival rate. So they should be treated as outpatients. But it turns out that the reason why they had a very high survival rate was because they were already treated like a lot earlier. So they come into the hospital a lot for checkups and things, and they were discovered a lot earlier in the process for heart disease. This was a correlation, but definitely not a causation. So one of the problems with deep learning is that it's hard to interpret what made it come to this decision. But if you'd realize that the system says if you have asthma, you're going to survive, then you realize that you maybe should take another look at your data and what it's actually figuring out. So they luckily figured this out before it was released, and they could remove a few things. So, so one way to do this is through looking at interpretability of systems. So this is a Python library called Lime. Lime means local interpretability of model explanations. And in this case, what they had was, as their test data, they had a number of images of huskies and a number of images of wolves. And they wanted to do a classifier between a husky and a wolf, but they had intentionally taken a lot of snow pictures of wolves and a lot of non-snow pictures of huskies. So this was a system that gave like super high accuracy. And when they asked people, okay, so how much do you trust this? Obviously, they trusted it a lot because it had very high accuracy. But what Lime can do is it can take any given picture and say, these are some of the pixels that it gave me, like that I used to inform me that this was, for example, a husky or a wolf. It uses some mechanism with super pixels and things like that, where it kind of like blacks them out and does like combinations of blacked out pixels and not, and see if it still classifies it as a husky or a wolf. But it's pretty cool because it can tell us now two things. A, we shouldn't be trusting this model because it's learning snow. right? And this is super common. It's super common if something learns the background, for example. But it also tells us that we could fix this classifier if we remove the background. So if we first use some kind of segmentation, remove the background, and then let it train only on the dog's face, for example. And we can iterate like that and make the model a lot better. So interpretability is a very good thing. Even if you have a system that, okay, now I think I'm good, the interpretability is also something that you can use on the client end of your application to say, hey, I think you should operate on this patient, and these are the few things that I found that makes me think you should operate on this person, which means that the client will be a lot more secure in using this decision or using this suggestion. Here's another example of Lyme where it's taken from a database called 20 news groups, where you get a lot of text from different news groups, and one of the topics or one of the objectives is to figure out which news group does this text belong to. So they tested it on this, and this is just to show that Lyme is not only for images, but it works on text as well. So in this case, what they found was that when they were to classify between the atheism news group and the Christian news group, they used those two because oftentimes they talk about very similar topics, so it's two very hard news groups to distinguish between. They found that .edu was a great feature to say that it was in the atheism news group. And in fact, if the message came from someone called Keith, it was always in the Christian news group because he only posted there. So obviously, again, we found a feature that doesn't generalize. It doesn't work in the real world if we were to classify between these two things. And we can now mark out that, okay, so this is what it found, but I don't trust this model. And we can, again, reiterate by taking away, for example, the headers and let it retrain on only the data we want to retrain on. So using something like Lyme or other tools is good for figuring out basically how you should reiterate and make your model better. If we go back to the face recognition, I mentioned that it's based on data that's it's actually the benchmarks of the Yahoo News data is 77% male, it's 80% white. The most common person in this data set, the one that gets classified the best, is George W. Bush, because obviously he was a very prominent figure in Yahoo News between 2008 and 2012. In fact, a lot of these data sets, this is just one example of a data set that kind of reinforces our hierarchies in society, basically who gets shown in news, who gets talked about in press and everything like that, and that is what we train on. So when we train on things like that, we're not necessarily representing everyone that's going to be a client of our systems. We're not representing black females. In fact, most black females are not even visible to face detection. So I put that up there. So one example of a problem when you use a system like this is what Nikon ran into when they created a system that's supposed to say, if someone blinked, don't take a picture. But then when using it in Asia, because it's not trained on Asian people, then it always thought someone was blinking. It's a very poor experience for these systems. This one, you've probably all seen it. It's not a very nice experience for them. And this is Joy Bulwamini. She's done a lot of research around this type of stuff. And one of the problems she detected was that she was just not visible at all to face detection until she used a white mask. Before, she always used a white mask in her research. Again, not a very nice experience. And one of the things it can lead to, this is a news article from Metro Code UK in July this year, where this one guy, a young black male, was stopped because he was on a watch list, and it turned out that the face detection thought it was someone else, someone from a watch list. And just to kind of explain what happens here is that if you think about, like, if you've only seen 2 chihuahuas in your life, you will not be able to distinguish between them because you don't have enough features to kind of like even understand. Or I'm not going to say even chihuahuas, like, what if you haven't seen enough people from, I don't know, Somalia, for example? You have a very hard time distinguishing between them because the features that differentiate them are not the same features that differentiate like Caucasian females, for example. And the same thing for machine learning. If it hasn't seen enough, it will not be able to differentiate them. So I'm just bringing this up as one of the things that we need to think about as we do these things. Another one is also kind of based on a problem because we're training on material that's very old, that has biases that somehow or I hope that we're trying to get away from these biases, but they're still, because we're using royalty-free data sets that are maybe 20, 30 years old, it still reinforce biases that we used to have. So this is Google Translate, actually, yesterday. If you put in, she is a computer programmer and he is a nurse, and you translate it to Turkish being a gender-neutral language, and then you just translate back, this is what happens. I'm saying Google Translate because Bing Translate actually introduces a word that is gender non-neutral to avoid this thing. I don't know if that's the best way to do this, but that's a way to do this. But these are hard topics. This is not an easy thing to do. It's not easy to understand that this will happen. It's not like Google actually intentionally made it happen. I just want to point out that this does happen, and this does affect a lot of things. But I don't want to end on a somber note, because deep learning, as you saw in the beginning, it can do a lot of magic. It can find missing children. I'm working on projects where we're doing cancer detection. It simplifies our lives every day. So I don't want to leave you on a somber note. I just want to give you sort of like a little piece of critical thinking that you shouldn't always take things for face value, but be a little bit more critical about them. And if you do want to delve into deep learning, this is the book. Like, no contest. Francois Chalet is the guy who wrote Keras, and he has a very, very good explanation for everything from structured learning to convolutional neural nets and recurrent neural networks. So with that, I leave you, and I thank you so much for coming and spending this hour with me. Thanks. We do have maybe a few minutes if someone does have a question, by the way.
How do you see the current state of deep learning in medicine and cancer detection?
Could you say that again?
How do you see the current state of deep learning used in medicine?
How do I see the current state of deep learning used in medicine? So, good. I think the key is interpretability, and the key is making like simple models. But it's quite an exciting time, for example, for something like cancer detection, because we just recently gotten to a point where we're doing digital and like digitalizing things like microscope slices and things like that. So I think it will flourish in the next few years, but it's very important to make the models very transparent and also recognize when there is false positives, that there is always like a human in the loop, someone that double checks the work, but maybe use the way, and what we're doing is basically just assisting to make things quicker, not saying a definite yes or no, but just being an assistant to make things quicker to discover. Yes. Did that answer your question? Yeah. Cool. Thank you.